Okay, so the next part of this theorem is a little bit more complicated. I don't want to prove it for you, but I want you to read it yourself. But let me at least tell you what the content is. So when later we learn about the Lagrange theorem tells you that if G is a finite group, it's a group, and it is finite. And if I know H is a subgroup of G, then we know that the order of H should divide the order of G. This will come later. If I have already shown this theorem for you, then this result that we proved was just a particular case of this theorem. So, for example, if I have a group, if I give you Z, if I give you a group whose order is 6, yes, for example, and if I tell you that H is a subgroup of G, and then I tell you that order of H is 4, you understand that I am wrong. Yes? Because if we believe the Lagrange theorem that we will prove later, is that this order of the subgroup should always divide the order of the group itself. So this means that this cannot happen. But if I say that order of H is 2, it might be true, might not be true. The problem is that I cannot guarantee, it is not contradiction because 2 divides 6, but it is not guaranteed that I really have a subgroup of order 2. You understand what is the difference? So in this case, I know exactly that this is wrong. So what happened? So I know that this is wrong. It is not. It's in contradiction with the Lagrange theorem that we will learn later. But if I say order of H is 2, on its own you cannot see any contradiction because it is consistent with the Lagrange theorem. But it still doesn't mean that you definitely can find a subgroup of order 2. It might be true or might be false. Is that right?
So it's not an equivalency, is what you're saying?
No, it's not equivalent. Yes? But when it goes to cyclic groups, it is also guaranteed. So it means that if G, order of G is 6, G is cyclic, yes, and then it is guaranteed that G has a subgroup of all divisors. For example, 1 is a divisor, 2 is a divisor, 3 is a divisor, and 6 is a divisor. These are the only divisors of 6. If G is cyclic, it is guaranteed that G has exactly one subgroup of order 1. You already know it. What is that?
E.
E. Only E. It has exactly one subgroup of order 6. You already know that.
It's G.
It's G itself. And it has exactly one subgroup of order 2, which you don't know yet. And you have exactly one subgroup of order 3. So that is the importance of being cyclic. And this is the theorem. Okay? So I want you to learn this yourself. Yes? Yes?
Does that mean it has one unique group, or can they be like the same? So maybe
No,
two,
unique.
three.
That's what I'm saying.
Unique.
For all divisors, for every divisor, you have exactly one unique subgroup.
So 2 and 3 can't generate the same group in this case.
No, these are, no, be careful. These are divisors of 6. These are not generators.
Yes.
I don't even know what is inside G. I don't know if it's in G are numbers. I just have an abstract group. I know something. This abstract group is cyclic. Okay, and I know its order is 6. If I ask you what are the positive divisors of 6, these 4 numbers. Okay, it is guaranteed by the second part of the theorem that you have exactly one subgroup of order 1, one subgroup of order 2, 1 of 3, and 1 of 6. This is what this theorem is claiming, and it is even more than that. It is telling you the generator. Okay, so let us see that. So what is the generator? So G is this subgroup, cyclic, and order is n again. D is a positive divisor of n, then G has exactly one subgroup of order D, and it is telling you how to find it. A to the power of ND generated. Yes? N over D generated. Is that clear? So for example, let me go to the board. In this case, for example, let me say that G is generated by A, for example, okay? And these are the divisors. If you ask me what is the subgroup of order 1, what do? I would write A to the power N divided by D, which is this one. Yes? And can you tell me what is this one? The order is 6. So what is that? E. Yes, because A to power 6 is E. And this is your E. Yes? Can you tell me the next one? So you see that the order is 1. Okay? What is the next one? This A to power 6, but this time divided by 2, which is A to power 3. If you want to open it up, it becomes E and A3 to power 1, but A3 to power 2, which is E again. So end of story. Yes? If I ask you, can you give me the subgroup of order 3? You would say yes. You would write A to power 6 over 3. So then it becomes A to power 2. And then if you want to open it up, it becomes E, A to power 2 and to power 4. Okay? And if I ask you what is A, the next one, to power 6 over 6, which is A, but this is just G itself. Yes? But what is G itself if I want to expand it? It is E, A, A2, A3, A4, A5. So you see, it is interesting. You see, these are the only subgroups of this bigger group. I mean, these are the non-trivial ones. If you pick this one and this one, it will work as a subgroup. If you pick E, A2, and A4, it is still a subgroup, but not any other combination will work for you. Is that right? It's not obvious. I want you to sit down. I think the proof is in the book. If you have problems, we can communicate and solve. Might be I can make a video. The way that I was proving it this morning in my head was a little bit different from. My way is more calculational. Because that's also, for me, it's easier because I have a lot of formulas in my head, so it goes very straightforward. Okay, any questions? So, for example, let me ask you this question. List all subgroups of Z sub 30. By the way, when I write Z sub 30 and I don't tell you what the binary operation is, there is a convention going on. What the binary what binary operation is here?
Something with modulo. I don't know which one, but
No, but which modulo? It's very clear.
Additive.
The only number appearing here.
Addition modulo 30.
30. Yes? So in principle, do you remember what is Z30? Z30 is starting from 0, 1, 2, 3, up to 29. This is Z30. Okay? Do you know that Z30 with addition module 30 is an abelian group? We had this before. Okay, and if I ask you what is the identity element, it is 0. Yes? So what is the inverse of, let us review. What's the inverse of 1?
29.
29. Because 1 plus 29 is 30. What is the this one? The inverse of 2? 28. What is the inverse of 0? Of course, 0 itself. Okay? So now the question is that, by the way, it's not that easy. I want you to see that if I ask you just randomly find all subgroups of this, you don't have any systematic way to do it. But now you have. Why? Why this theorem is useful for my case here as well? Because this theorem that I just described here for you only works for cyclic groups. Yes? Nothing else. So it means that if you want to use this theorem, which we want to, we have to first confirm that this one is indeed a cyclic group. Yes? Is it cyclic?
Yes.
So why? When you say that, when I say why, you have to present a generator for me. Yes, please?
I mean, you can take one and just.
That's enough.
Yeah.
One generates everything. Yes? So as soon as you have one generator, that is not the only generator, but of course we have one to that generator, so it is a cyclic group. So this means that this theorem is applicable. Tell me systematically, if I want to organize all subgroups, because it is cyclic, so important if you're taking notes, so cyclic, okay? And then you can write Z30 is equal to what? This one. Yes? Okay, so it's a cyclic group. But I want you to tell me, first of all, tell me how many subgroups you expect. How many subgroups do you expect? Yes?
8.
Why 8? You are counting
Yeah.
the divisors.
Yeah.
Exactly. It's a 30, the divisors of 30 is 1, 2 is another divisor, 3 is another divisor, 4 is not, 5 is, 6 is, then the next one, 8, 7, 8, 9, 10, 15, and 30. These are the only divisors I have. 1, 2, 3, 4, 5, 6, 7, 8. So there will be definitely how many subgroups? 8 subgroups. And if I insist you to find them, how do you find them? I want you to make sure that you are not confused with the notation now, because you already know. So, for example, can you tell me a subgroup of order 3? How many, by the way, let me ask you another question. How many subgroups of order 3 I have? 1, because of that theorem. Okay, and I want you to tell me which one is that. So, subgroup of order 3. The formula is here on the board. So you have to write your generator, which is 1, to the power n, in this case, 30, divided by, I want you to give me order 3, so you have to divide by 3. Yes? Is that right? But this is a little bit confusing. Can you continue for me? So this becomes what?
1 to the power of
10.
10.
But 1 to power 10 in the addition, in the multiplicative notation, which means what?
10.
10. Do you remember? So this 1 to power 10 is not 1, is 1 binary operation with 1, binary operation with 1 10 times. But what is my binary operation? Addition. So it becomes 10. So be careful, it's a little bit tricky. I hope that you are not confused with the notation. So 1 to power 10 is 10. And if I ask you what is this one, just generate it for me. The first one is 0, the next one is 10, the next one is 20, and that's it. This is your subgroup. Is that right? So it is a very, very strong theorem. So it is giving you a systematic way. By the way, it's a very, very hard problem in mathematics to categorize all subgroups of a given group. That's a very sometimes active research to find all subgroups, okay? But for the cyclic groups, the problem is solved. Everything is settled down. Is that right? Yes? Okay, good. So let us now go to the next part. This is a self-check point. So I don't know how much I have to spend on functions, a quick review. I wrote before that I was expecting you to go and read it yourself. Okay, I hope that you have done it. But let us go very quickly. Okay, very, very quickly. So about functions, what do we have of a function? Function is a rule of assignment. So I have two group of elements. I start assigning one element from the second group to every and each element of the first group. But in a way that I assign exactly one element to each. So it's very complicated. So let me write here. I have two collection of things. So let me call this collection of things A, and I call this collection of things B. Yes? Okay, by collection, in a more proper language, I would say set. Yes, I have a set A, I have a set B. I have some elements in A, yes, and I have some elements in B. So let me call them A1, A2, A3, A4, okay? And then B1, B2, B3, B4, B5. When I say that I have a function, it means that you have to make connections between these elements and those elements, but there are some rules to respect if you want to give me a function. The first rule is that, first of all, you have to bring one single arrow from all of them. You are not allowed to leave one of them empty. So it means that I want to take arrows starting from here, terminating somewhere on these points. Okay, but I have to respect the rules. The first rule is that I have to give them the same share, equal share, and that share is exactly 1. So one arrow should go out from each and every element of the one on the left, but you don't have any restrictions on the elements on the right. So for example, I can connect all of them to B1. Yes? So it's very hard to draw all these pictures. So I can connect all of them to B. Yes? This is a function for me. It's a rule of assignment. So, okay? So, for example, I can call this function function f. This has a name in mathematics. What is the name of this function? What's the name of this function? Everything is going to B1. So it's called the constant function. So no matter what you put in, the output is B1. So if you want to compare it, it's like dictators. So it doesn't matter what you say, they always say the same thing that you want to say. They don't care what you put in, they just say B. Okay, so that's a constant function. But there is no restriction. But this is not acceptable. This is not acceptable. Yes, because everyone should receive exactly 1 arrow. That's not acceptable. So if you have this is not a function at all. And then this set has a name in mathematics. What is it called? It's called the domain. Okay? And this set is called the codomain. Okay? So look here. So if I want to show that I have a function from A to B, I use this symbol. This is red. F is a function from the set A to the set B. This is the way we read this symbol. Okay. This is the domain. So I would write it by domain of F. I don't remember what is the standard name for codomain. So let me just write codomain. But I have also an important point of a range or image of a function. So you see, if I draw this picture, do you agree that this is a function? So let me write it in a way that I can draw the picture nicely. So I will take this one here, I will take this one here, and I will take this one also here. Okay, I hope that you're not confused. These are simple things. If you don't mind, let me just mess around a little bit. Okay, so if I ask you what is the domain? A. What is the codomain? B. But what is the range or image? It means the collection of all the points who have received at least 1 arrow. Okay, so this is the range. Okay, so that's called the range. The range is those ones who are receiving at least 1 arrow. That's called the range. So the range is usually might be smaller, is a sub-collection of the codomain. Yes? And very simple now. If this becomes as big as the codomain, the function is called? The function is called surjective. Yes? Or onto. English name, both of them are onto. So it maps onto the whole B. Okay, so I will use this word, it's easier. But this is the correct word, surjective. Okay? But we also have another one, which is injective. So injective, this is not injective. Injective means the elements in the codomain either shouldn't receive any arrow or at most 1 single arrow. Okay? So this is receiving 1 single arrow, good. This is receiving 1 single arrow, good. But this one is receiving 2 arrows, so it is not injective. Okay? So if I want to make it injective, I can take this one and connect it, for example, to what? Connect it to B4, for example. This is now injective. Yes? But now I want you to develop, I'm going very fast here because I hope that you can read it yourself. If this function is f, what is the name of B1? Technical name. B1 is called the image of A1. Okay? And how I note it, I write B1 is equal to f of A1. Okay? So it means that, or some people write A1 goes to B1 under f. These are the notations we use. And the name is that B1 is called the image. And by the way, sometimes range is also called the image. I have written all these terms here for you. Okay, so now I want to ask you to write, so we have two things, onto, surjective, injective. What is the other name? It's one-to-one. And I'm lazy, I write it like this. Okay, so it's a one-to-one. So is this function a one-to-one or injective? Yes, because none of these are receiving more than one arrow. But is it surjective?
No.
Surjective means every one of them should receive at least one arrow. Some of them are not covered. Okay? So now, can you tell me, if I want to have a mathematical definition of injectivity, how should I write it? Let us say that f is a function, df is its domain, and I want to tell you what is the meaning of injectivity. So how can I define injectivity? So I would say that for all x1 and x2 in the domain, if x1 is not equal to x2, if I have two different elements, they shouldn't go to the same element. They should go to different elements. It means if x1 is not x2, then f of x1 is not equal to f of x2. And then you know that in mathematics, whenever you have p, then q, it's always equivalent to saying what? If not q, then not p. It's extremely important. You have to think about it. This is mathematical logic. I mean, this is logic. Okay? So this is called the contrapositive of that one. If you just change them, that is called the converse, not the inverse. Okay, that's a converse. And that converse is not usually equivalent to the statement. It might be true or might be not true. But this is always equivalent. Okay. So now it means that I can change them and do the contrapositive. So some books, they define it in the other way around. So they put this first, but negate it. So can you help me? It becomes what?
If they're the same, then.
If they are the same, then these are also the same. So both of them is good to remember. Sometimes one of them is more useful than the other one. So that's the meaning of injectivity. Okay, that now you have the understanding of the onto function, surjective function. Can you give me a mathematical definition? So if A to B is surjective, if what? I want you to define mathematics. Yes, please.
It's the I don't know if it's called size or order of the domain and the range is the same.
So it means if range of f is equal to b. Yes, that's the meaning. So the b here, it is not onto because this is not covered, for example. So it means that the range is smaller than b. But if it is the same size, you know what I mean. Same size is not a good correct. I mean, it's exactly the same, so this means that's surjective. Or if you want to make it explicit, what does it mean? It means that for every y, can you complete it for me like this? For every y that I choose in B,
It's also in R, right?
no. I want to define the same concept by a little bit more expanded version. This is completely good. For all y that I choose in B,
It's the image of something in A.
so it means mathematically.
There exists.
That exists, thank you. X
So that's
in
in
A such that
y equals f of a.
y is equal to f of x. That's also the surjective definition in a little bit more expanded version. Is that right? But something that in algebra is very important is this one. So I want you to understand, this is extremely important, you will see in the future, well-definedness of a function. Okay? So what I have written on this slide, does the following rule define a function from Q, a set of rational numbers, to Z? Because I want you to see, we want to make sure that what we are defining is correct. So it means that, by the way, if I ask you, if I insist you to define a function mathematically, how do you define it? So what was the rule? The rule is that for every element, there should come exactly one arrow out. If you want to formalize it in a mathematical language, what do you say? You say for all x1 and x2, where in the domain, if x1 is equal to x2, it means that if these 2 points are the same, they have to be imaged to the same point. So this means that f x1 should go to exactly f of x2. This is well-definedness. Yes? This is well-definedness. So now let us go back. Oops, I forgot to record this part. Anyway, so now if I go here, f of a and over b is equal to a plus b. And I am telling you that is this rule that you see on the board is a nice way to define a function. This becomes important in this course. Do you think it's a well-defined? So it is telling you that f, apparently, I mean, this is not a function because you will see this is not a function, so that's not the correct notation to write. But anyway, do you think if you see this in the board, do you complain or you're happy with it? Yes?
complain.
Complain. Why?
A counter example would be 3 and 2, and then 6 and 4.
Yes, let me make it simpler. 1 over 2 is equal to what? 2 over 4. Everyone agrees with that. But I told you that if this is going to be a well-defined function, as soon as I have 2 equal numbers or 2 equal elements from the domain, the images should also be the same. Yes, that's not a very good way of defining, because if I ask you what is f of 1 over 2, you will write 1 plus 2, which is 3. And if I ask you what is f of 2 over 4, you will say that it is 1 plus 2 plus 4 is equal to 6. And they are not equal. So I mean, when you want to define a function mathematically by formula, the only thing you have to be careful about is this. This didn't happen in calculus, yes? Because for example, when I write f of x equals to, I don't know, even if I give a complicated function, the third root of x to the power of t ln of x, I don't know, plus sine x, something like that. Okay? So if I choose any number there, how many outputs I get if I do it correctly? For example, if I choose x to be 1, what is the output? It will be, this is 0, this is 1, this is sine of 1. It will be 1 plus sine of 1, and that is a fixed number. Yes? So in calculus, this doesn't matter. Yes? But in this course, it matters because sometimes we have 2 different things, apparently. These are different symbols, but for the same entity. If you want to define a function based on this, you have to make sure that the images will also be the same. But have it in back of your head, you will see why this becomes important. But at least I hope that you understand this is not a well-defined function. Is that right? Any questions? Okay, so the next one, okay, this is very good. Tell me, because most of them you already know. If I ask you what is the meaning of the functions be equal, I give you 2 functions, f and g. Okay, be careful. This equality will be between 2 functions. Functions are rules. These are not numbers. So you have the minced, how do you say, the machine that make the minced meat. You put the meat there, the minced meat come out of it. What is the function? The apparatus itself. The function is different from the input and output. Okay? So when I say F is equal to G, it means the machines are the same. They are acting, they are operating the same. Yes? So I have my laptop, you have something identical to laptop. So we can say that these two machines are the same. Okay? Okay, when do I say that these two machines are the same? Why? When two functions are the same, two rules. Extremely important to remember. Two rules. The first rule is that the domains should be the same. Yes? So we say that this is the case if and only if two cases. One, the domain of F is equal to domain of G equal to some set. And then number two, for every X chosen from this common domain, F acting on X and G acting on X are the same. Usually in calculus, so for example, if it is a question in calculus, this function and this function and this function, are they the same? Are they equal? The first impression is that yes, all of them are equal to 1. But I want you to see that no, this function and that function are equal, but this function is not equal to any one of them. Why? Because what is the domain of this function based on your calculus course?
Real number.
The domain, yes, everything. Every number you can feed in, the answer is 1, the dictator. Yes, that's 1. But do you have any obstacle here? Is there any exception for x here? No, every x you can put here. So the domain of H and the domain of F, both of them are equal to what? Equal to R. And the values are the same because it doesn't matter what x you choose, the result of this calculation is 1, the result here is 1. But I cannot say that this is always 1 because there is an exception. What is the domain of G? The domain of G is R minus this 0. Okay, so this means that G is not equal to these because the domains are different. So it is important to respect the domain and equality of the values. Is that right? Okay. I forget to record, I don't know why. So the next one, I have already talked about that. And then, oh, I have to fix this. Okay, so for example, let me do one of these. I will fix this bad thing here. So I have given you this function. Let me do one example here. F of F goes from R minus, what is it? Minus 1 to R. Okay, and then I have defined F of X to be 2x plus 1 and then divided by 1 minus x. And I'm asking you to show that this is injective. Okay? So how should I show that this is injective? So what is the domain? Do you agree the domain is correct? Because 1 has a problem here. So this means that I have to choose x1 and x2 in this domain. And I ask myself, does f of x1 equals to f of x2 implies the equality of x's? The definition is on the board, yes? Of course you can use this one, but for this kind of functions, this definition is more suitable. Do you agree with me? That is, so I want to ask myself, I pick a pair from the domain, I assume this is correct, and I ask myself, is it possible to go forward and conclude mathematically x1 equals to x2 or not? If that is true, then it means I have proven that the function is injective or one-to-one. And if you feel it is not true, you have to bring a counterexample. Okay? So, but what do you think? Yes?
If it's true or not, or how
Yes?
to do it.
Yeah, do you have any feeling? So let us do that. F of x1 equals to f of x2. What does this mean? It means that 2x1 plus 1 minus x1 is equal to 2x2 plus 1 minus 1 minus x2. Do you agree? F of x1 means this, f of x2 means this. But can I, some of students I have seen, they jump into the conclusion and say, okay, so everything is similar, so x1 should be equal to x2. Yes, this is not correct. You have to prove it. For example, if I give you sine of x1 is equal to sine of x2, so let me write it like this. Sine of x1 plus pi over 9 is equal to sine of x2 plus pi over 9. Yes? Everything is, they look similar, so you draw this conclusion that, okay, x1 should be equal to x2. No, that's exactly the point. We have to conclude that. So what do you think I will do? I will multiply this like this, because these fractions are equal. If this multiplied by that, multiplied by that. So let us do it in our head. This becomes 2x1 plus 1 minus 2x1 x2, and then I have minus x2. Then it becomes equal if I multiply them. So it becomes 2x2, and then minus 2x1, and then I have 1 minus x1. I'm just simple algebra. This multiplied by that, this multiplied by that. But what happens now? If I move this to the other side, this will cancel that one. This one cancel that one. And then I move x2 here, it becomes 3x2. I move minus x1 here, it becomes 3x1. Yes? And then you can see that I can divide by 3, and I am concluding this, not guessing. So this means that if you believe this is true, then you have to believe that x1 is equal to x2. There is no other way. So these kind of things, you have to know what to do, okay? So let me see what else we have here. So I have already defined for you onto and surjective functions. I want to skip this. I don't know why this has happened. I will fix this. This is probably my coding is wrong. Okay, so let me skip these ones. Okay, you can do this. I skip, but you don't skip, please. Go and see if this is surjective or not, or find B so that it becomes surjective. This is the problem, yes? Here you see I want to fine-tune this set codomain B so that this function, which is the same function, becomes surjective. Okay? That's up to you. What does it mean? It means make B equal to the range. Okay? So for this course, this is not very important. But you have to have a good feeling about what is the meaning of range, or what is the meaning of surjectivity, injectivity. But because you are already familiar with calculus course, this is why my examples are from there. But this is not that very important here. The concepts are more important. Okay, so now let us go to the next one. Bijective. What is bijective? Have you heard about that?
Yeah, it's both.
It's both. Yes, and there is a terminology here. If f from A to B is called bijective, if it is both injective and surjective. In this case, we also call f a one-to-one correspondence between A and B. So we can say if f is bijective, I would say that f establishes a one-to-one correspondence between A and B, set A and set B. So can you tell me, if I have two finite sets, A and B, and if I have a function from A to B which is onto and which is one-to-one, okay? If A and B are both finite, something can be said about set A and set B. What is that? If I have, yes?
They are the same size.
They are the same, they have the same cardinality, they have the same number of elements. So if two sets are finite, yes, and I can establish a one-to-one correspondence, meaning that if I can find an onto and one-to-one function from A to B, it means that I have already shown that the elements, the number of elements in A, the number of elements in B are the same. Cardinalities are the same. Okay? So this one you also do that. Okay, and then the composition function. Do you know the composition function? Yes, hopefully you know that. So I will skip this one. And this one is also good to know in this course. What is the identity function? I just want you to know the terminology and the notation. So if you have a non-empty set, non-empty set, but there are different symbols for it, but this is very standard. Identity function on set A, first of all, is a set from A to itself, and unless, in contrary to the constant function which was complete dictator, this is completely liberal. So what does it mean? It means that whatever you put in this function, it agrees with you. Yes? So you put A in, it gives you A. So it is contrary to that dictator up there, which we can remember. It's an identity function. But do you see that the identity function is a one-to-one correspondence between a set and itself? Of course, yes. It's all, both on-to and. But be careful. Identity function, these two should be the same set. Yes? Can you give, before going to the next slide, can you have a feeling about what is the role of this identity function? So let me here. So let forget about this. If f is from A to B, and tell me if I have an identity function, exactly what you see on the board, what is the relation somehow between them? By the composition function, I mean. Yes?
The composition of the identity function with another function is always the other function. So
the other function, but you have to be careful. Why? Because do you think that this makes sense or not? Identity function OF. This doesn't even make sense. Why? Because F takes you from A to B, but then identity is going to apply. So for example, if I give you A, what does it mean? It means F acts on A, and then identity should come and act on this. But this is not possible, because when F acts on A, it takes you from A to B, but identity cannot apply on elements of B because identity on A should apply on A. So this is not even well defined in this case. But if it is defined, what you said is correct. For example, in this case, which one is defined? The other way around. So FO identity is equal to F. Yes? If I insist to write something like this, can you help me? Here I have to put F on the left. But if I insist to put F on the right, yes, please?
the identity function on B.
On B. So then it becomes identity function on B is F again. So it is not the identity element as group, because it might be the left one or it might be the right one. The identity should work from left and right simultaneously. So that is why it works for the functions from the same set to the same set. So we cannot talk about is the set of all these functions is a group or not, because they are not. Mostly the identity element works in one way, not the other way. Yes? Understandable or not? Okay. So I have written everything here. What about the inverse function, by the way? So inverse function, so you see f from A to B, be a bijective. That's a definition. There is a theorem guarantees that if you have a bijective function onto one and onto, there is a function, there is a unique function g, so that in this previous theorem, there is a unique function g so that when g acts on f from the left, it gives you identity on A, and if it acts from the right on f, it gives you identity on B. If f is a bijective function, I want to give you a feeling about why this theorem is correct. Okay, so let me give you a feeling, might be it is easier. So, can you tell me simply, if I give you a function, okay, so you see inverse function, let me make it simple, I don't want to make the diagram complicated. Do I define the function here for you or not? Is this diagram of function? Yes. The inverse function is going to be a function that undoes whatever f does. Okay, so what does it mean? It means I want to reverse the arrows. That's it. Okay, if I want to reverse the arrows, then you will see that I have a little bit of problem. the original function, I agree with you, that is a function. Okay, but can you see that, oh sorry, the other way around. So, can I say that the green arrows is defining a function from B to A?
No.
I'm just reversing, why not?
Because there's one dot.
Because one dot is empty, and that was not the rule for the function. Every element should have one arrow going out, exactly. So this means that, why do you think this is a problem? Why this is a problem? Because my original function was not on 2. So being on 2 is important, because this one doesn't receive any arrow from my original function. That is the culprit. When I switch the arrows, one of them will be left empty, which is against what I have this rule. Okay, but now let me tell you another one. So you see that being on 2, surjectivity is one ingredient you need to be in place. But now let me do it a little bit differently. So here I have, so let me draw it in this form. Here, 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 and then I have these two. So let me this time keep surjectivity. Now I will have this one, and I will have this one, and I will have that this one. Sorry, so let me clean this. Okay, so tell me, is this a function or not?
Yes.
It is a function. Is it surjective or not?
Yes.
It is surjective. But let me again reverse the arrow. You will see I am again in trouble. Yes? If I reverse the arrow, this will be this arrow, this will be this arrow, but this will be this arrow. But this is not even a function, because from one of them, more than one arrow is going out. So you see that in order to reverse the arrows, yes, and keep the definition of the function in place, I need my original function to be both onto and one-to-one, bijective. Okay? But as soon as I have bijectivity in place, it is very easy to imagine you can just reverse the arrows, that's it. Is that clear? Yes or no? Okay. So, yes. So I will skip these. Or might be I will talk about the last two parts. But I want you to, I will write on the Canvas page which ones you want to do. As before I told you, these kinds of questions are also in your book, but they are not that important in this course, okay? Might be, unless they are combined with a little bit concepts from abstract algebra. But of course, you have to be able to manipulate. For example, you should be able to immediately find the inverse of this function, which is a problem in calculus, not in abstract algebra. But you have to know these things. Okay, so there are some other things. I will talk about these things. So I will, these two theorems are important, okay? And then I will have groups of permutations, okay? I know I went very fast, but please, when I write something on Canvas, if you study this, I think these are very simple, okay? So it's very fast. I hope that, but I will concentrate on the last 3 slides next time, and then we start permutation. Okay, but then I have to somehow go very fast. I don't know how to manage to go faster, okay? So let me stop here.